All right, so we're going to talk about multicast VPNs. So before we get into it, let's just kind of refresh our memory as to what is multicast. Anyone got any suggestions as to what is multicast? We're sending traffic, we're sending data to a group of receivers. All right, so unicast is from one to one, broadcast is from one to all, multicast is from a single source to a group of receivers. Okay, so the main point is that the receivers belong to a group, all right, and the traffic is directed to a group. So the way that a receiver gets multicast traffic is by becoming a member of the group. Right now, a really good example of that is IPTV, okay, Internet Protocol TV. So if I am receiving a stream of broadcast traffic, just say I'm watching Channel 9, I'm receiving a stream for Channel 9. If I take up my remote control and I go click and change the channel to Channel 10, then what I've done is I've left the group, the Channel 9 group, I've joined the Channel 10 group, and I now start receiving Channel 10 traffic instead of Channel 9 traffic. Okay, so every time you flick through a channel, you're leaving a group and joining a group. So there's this multicast leave and multicast join requests that are sent out as part of that process. Okay, so the goal, the challenge now though, is let's say I'm a television provider. I'm a television channel. I wish to provide television services to my customers. Of course, how do we do that? Well, currently we have an antenna sitting up on a hill where we broadcast everything out. Okay, that's fine. But what about the mechanism where we want to distribute this same television through the internet or through a network, through an IP network? Okay, because that really is the future, right? There will come a time when we no longer have an antenna on a hill, right? It will all be distributed through a network. In Europe, that's very much that way. Everything comes through a fiber that connects to your house in many places. So what we're going to talk about now is what is the mechanism that was going to allow a provider of television or some other type of multicast traffic. Radio stations do this as well, for example. There's radio stations that you can get internet radio and they will multicast their radio broadcasts. So what we're talking about is, with this multicast VPNs, is how can we provide a mechanism where the provider of this broadcast, or this multicast really, this multicast has a mechanism for distributing that through the internet, and how can the provider provide that service to that particular television source, that source of multicast traffic, because this may span, I mean, this provider's network can span an entire country, for example, or entire city. There's providers that have the networks well up and down the east coast of Australia, for example. How can we distribute all of that through and do it efficiently? So let's just take a look at a few concepts here. We're going to look at the flow of control traffic and data traffic in what's called the next generation multicast VPN. By the way, the reason it's called the next generation is because there is a way that it has been done for many, many years, and that way that has been done has some major problems when you want to expand it. So it's very limited, doesn't scale very well. So this is the new way. Talk about the new way. So describe the configuration steps for establishing this next generation multicast VPN, and monitor and verify the operation of this. So let's take a look at the overview here. So this is the model for the multi-service network. This is kind of where we're at right now. We've got layer 3 VPNs, we've got layer 2 VPNs, we've got virtual private LAN services over there, and there's other things as well which have also now been developed, and there will be other things in the future. So the way that we are signaling this, we're using BGP as our signaling protocol, and we're using MPLS as our transport infrastructure. That is different to the way that it has been done in the past. This is kind of like where it has been done, and probably still is being done in some places, where if we want to have multicast, then we use a protocol called PIM to facilitate the multicast. PIM stands for Protocol Independent Multicast. And so we use a protocol called PIM to set it up. This is kind of the way it has been done. And our transport infrastructure is then GRE tunnels, all right? Generic routing encapsulation tunnels. So we're not using BGP and we're not using MPLS. And the problem with that is we now have to run this whole extra protocol, PIM, in addition to, of course, BGP, which we're already running because a service provider must run BGP. So we're already running BGP. Now we've got to run PIM as well. And our GRE tunnels do not give you the flexibility, the traffic engineering, the failover support, or the redundancy that you get with MPLS. So you get a lot of high availability with MPLS that you don't get with GRE. Okay, so this is the downside of the way it's been done. The routers have to participate in the customers and the provider's multicast domain. The multicast traffic from the customer instance of PIM is encapsulated in a GRE. And the multicast data and the hellos, the joins and the prunes. A join is when you join a multicast group. A prune is a mechanism for the multicast network to stop sending multicast traffic down paths where there are no more receivers for that traffic. That's what a prune is. So we have all of these different multicast mechanisms that have to be distributed. And the PE1 and PE2 join configured VPN group addresses within the provider's domain using a provider RRP, so we'll look at that. So basically, the downside of this is that there's too much going on. It's not scalable, it's too hard to configure, it's too hard to administer. So we have a new way of doing it. There was an RFC come out which describes this, or actually a number of RFCs which describe this. And what we're doing is we're going to really leverage off what's already happening with BGP and with layer 3 VPN services. So we're really kind of leverage off what we're already doing. There is an increasing interest for multicast, in particular in IPTV. And as I was saying, as the current mechanisms for distributing television begin to converge with internet, as other things have, so we've already got voice, so the telephone network has converged into the internet, into the IP network. Most radio stations have some internet capability where they're distributing their radio stations through the internet. There are some radio stations that only do internet. They're total internet stations. But many regular broadcast stations are also distributing through the internet. And television is the next thing. The thing with television is it's really, really high bandwidth. And so it benefits greatly from multicast. We also have the ability to configure point to multi-point MPLS LSPs. So instead of just having a label switch path that goes from an ingress to an egress, it can go from an ingress to multiple egresses. Okay, so we have a point to multi-point. and the existing scheme, which is called the draft rosin scheme, because it was invented by someone named Rosin, has got limitations in that it's not very scalable. All right, so this is the next generation. So we're going to be using unicast and multicast layer 3 VPNs. We're going to be using our BGP for signaling and MPLS for our transport protocol. And we've got all that traffic engineering capabilities, all of that high availability stuff, bandwidth guarantees, all that good stuff that we get with MPLS. Okay, so replacing PIM with BGP. So the benefit of replacing PIM with BGP is that PIM is highly traffic intensive. It requires many peering arrangements between the PEs, and we're running BGP anyway, so we're already running it. So let's just use it to do the job that PIM has been doing. Okay, so we add, so what we're doing is we're actually expanding BGP, we're extending BGP to provide some additional network layer reachability information, the NLRIs, and that is going to be used for this multicast VPN signaling. So we're expanding BGP. We've got some additional capabilities. We've got this membership auto discovery for what's called selected provider tunnels, customer PIM join messages. So the customers are still running PIM between the CE and the PEs, and we're converting that across into BGP signaling, so we don't have to run PIM in the provider core. The benefit of that is the PE routers only need a few BGP sessions with route reflectors, and that can be achieved quite easily, and they can be the same route reflectors that we're already using anyway for unicast VPNs. So a bit of terminology. We have these things called PMSIs, which are a type of tunnel used to transport multicast data across the provider core. They can be an RSVP signal LSP. You can still use PIM if that's what the provider wants to do. Probably not though, but it's available. Or we can have this multicast LDP. Within the Juniper, so this is, we're talking what the RFC defines. Within the Juniper platform, we're really going to be doing just the top one, just the first one. Juniper doesn't support the multicast LDP. We have these IPMSIs, which are multi-directional sort of paths. So what happens is the PEs in an MVPN transmit multicast packets to all other PEs, and unidirectional enables only a particular PE to transmit multicast packets to other PEs. Then we have this SPMSI, where a particular PE can transmit multicast packets to a subset of PEs. So the first one is kind of everything to everything. All the PEs transmit multicast to all the others, and in the other one, we only have some PEs transmit a subset to other PEs. Why is this? Why do we do it this way? Well, because it's in the first one, the multi-directional, what we get is we get less peering arrangements, less configuration, less signaling state has to be maintained by the routers involved in this process. So one of the things with multicast is that it's different to unicast, because with a unicast VPN, the P routers in the provider core do not participate at all in the VPN process, whereas with multicast, the P routers do have to participate in the process because they are part of the multicast tree, and they are involved in the basically the splits as you go from the root down the tree. So they have to be involved. So these two mechanisms are kind of a trade-off between optimal multicast functionality and scalability. within the system. So what you tend to do is where you have some very, very high bandwidth multicast, you may use the SMSI, where we've got a particular PE will transmit multicast packets to a subset of PEs, and where you've got the lower bandwidth to save on configuration, to save on the amount of signaling and state and peering that the routers have to maintain, you will use the other. All right, so here we go. So we use this multicast VPN NLRI, or network layer reachability information. The format is in this new AFI 1/SAFI5, which is the format. It's just the format. Remember we had, when we were doing, looking at route distinguishers, we were using SAFI 128. It's just another format for BGP information. So routes get tagged with a route target community are placed into the BGP mvpn.0 table. So there's a new table, all right, that we've been introducing for multicast, and it will be the instance name .mvpn.0 table. So we have a new routing table that we're using. Next generation MVPN draft specifies some new attributes. So there's a P multicast service tunnel attribute, which identifies the tunnel in the provider core that this traffic is going through. So there we have an MPLS label in this case to identify the tunnel, and there's a tunnel ID. So there's a couple of ways that this is done. Type 1 is what we're doing in this particular course. This is one that's supported by Juniper. Type 1 is within a single autonomous system. So this is happening within a provider. Type 2 is where there are multiple providers involved in the multicast distribution. So it is possible for a broadcaster to say, I want to put my traffic onto the internet and do that through multiple service providers and have the distribution go across multiple service providers. It's possible. We're only going to cover that happening within a single provider in this particular course. And type 3 is the selective MVPN auto discovery route sent by a PE that initiates the SPMSI, and type 4 selective MVPN auto discovery route for leaf sent by the receiver PE upon receiving a type 3 with the leaf information bit sent. So this is really the mechanism for how do routers discover that they are part of a multicast tree. And these are the signaling protocols that enable routers to discover all of that. Type 5, source active discovery route sent by a PE router that discovers an active multicast source. So learnt through PIM. A register message, and there is a PIM between the CE and the PE. And type 6 is a shared tree join route sent by a receiver PE that receives a PIM join on a VRF interface. So quite a few different bits and pieces there. And this is the 7th one, is a source tree join route. So these are the new network layer reachability information that has been added to BGP to facilitate multicast. All right, so point to multi-point, this is the concept of it. So we have this is RSVP, point to multi-port. LSPs can be used as the transport mechanism for next generation multicast VPN traffic across the core. Traffic is protected using all the standard methods like fast reroute, link protection, etc. All the stuff we talked about earlier. So we've got a source there up at PE1 that gets down. PE1 goes down to P1. P1 then splits that down into the multicast tree. P2 splits it again, and it goes out to the egress PEs. Okay, so what we're talking about here is multicasting through the provider's core network. All right, so this is a mechanism where the provider, the service provider, is providing multicast out. So these PEs, PE4, PE3, and PE2, they could be in completely different geographical locations. One could be in Brisbane, one could be in Sydney, one could be in Melbourne, for example. And so we can then be distributing this traffic, which could be radio, could be television, out into different geographical regions. Could be different PEs within the same city, just distributing it out into different different customer bases. Okay, so we have these inclusive trees. Each tree serves one multicast VPN only. So all the multicast traffic in that multicast VPN arriving at the ingress PE is mapped to the same tree to get from the ingress PE to the other PEs in the same multicast VPN. So the benefit of this particular model is that you can have multiple sets of VPN traffic going down the same paths. And what that allows you to do is it allows you to limit the number of multicast trees that you need to establish in the provider's network. So you don't have a separate tree for every source. You can have multiple trees, multiple sources using the same tree. The reason for that is to achieve scalability within multicast. Okay, the downside of that is that you will get multicast traffic arriving to PEs that really don't have any receivers for that traffic. Now that is one of the downsides that you could potentially have for that. Selective trees, they serve particular selected multicast groups from a given multicast VPN. So that is where you never get any traffic going to a PE that doesn't have receivers for that traffic. The inclusive signaling example here. So we've got a provider core. We've got our source over here on the 10.0.101.2 there, that's being sent into the PE. So we've got the CE over here, and there would be generally this model presumes that we have got a PIM pair between the CE and the PE. Then we've got no PIM in the core at all. We're simply using BGP signaling with those 7 new network layer reachability, lots of information that we've added into BGP. And what happens is that the other PEs, through that signaling, discover what multicast trees they are a member of. They then join that, and they begin to receive that traffic. So prior to enabling the MVPN, the PE routers have an existing layer 3 VPN established using LDP to signal the LSPs. The provider core does not have PIM enabled. So we're simply using BGP in the core. So with no source or receiver's multicast traffic, a multicast VPN is enabled on the PE routers. Each PE router advertises an inclusive multicast VPN, which is this AD route to each other, tagged with a route target, and the PMSI tunnel attribute, which is the PMSI represents the label switch path that is going to be used to actually send that traffic. Automatically builds the point-to-point LSP to the other PEs with itself as the route, and we have got no PHP or virtual tunnel interface or VRF table. Okay, so they discover what multicast VPNs they are a member of, they automatically join it, and they automatically then build and signal an RSVP signal path. So the source against sending multicast traffic, CEA, sends register messages to PE1. PE1 is now aware of the active source. PE1 sends out the SA auto discovery routes to its remote PEs. They then receive those routes and they then join that particular group. So the receiver CEs send PIM source joins upstream to the PE2 or PE3. The receiver PEs convert the PIM join to MVVPN source tree joins, and the source PEs convert the MVPN source tree joins to PIM at the other end and send it to the DR to complete the multicast tree. So that's right across the core, right from the CEs right down to across the provider core to the PEs and then down to the receiving CEs. Okay, so this is kind of like the overview of how this works. Okay, then we've got the IP MSI forwarding. So after the tree is built, CEA sends a native multicast packet, PE1 encapsulates the packet in a single MPLS header. The outbound MPLS label is derived from the point to multi-point LSP. P2 sends copies of the packets to both PE2 and PE3, and the receiver PEs pop the outer label, send the traffic based on the VRF route on the inner label. Okay, so the signaling for selective is we set up layer 3 VPNs right across using LDP. No PIM on the core. Multicast VPN is enabled on the PE routers. Each PE router advertises an inclusive VPN AD route to each other tag with the route target. We have no point-to-multiple LSPs are built between the PEs at this point. As soon as the source begins sending the traffic, PE1 becomes aware of the traffic. PE1 sends a SA auto discovery route to its remote PEs. Using IGMP, receivers join the Pacific group. Receiver CEB sends a PIM source join upstream. Receiver PE2 converts the PIM join to MVPN source tree join, and no receiver gets attached to CE3 because there is no traffic for that particular receiver. PE1 completes the multicast forwarding tree. PE1 sends SPMSI auto discovery routes to remote PE, and only PE2 responds. Now, the thing with this selective is that it limits the traffic to parts of the tree where receivers exist for that traffic. That is different from the previous, where basically you can get traffic going to points where there are no receivers. So why have the two? Well, really, it's to limit, it's to enable scalability. This second mechanism, although more efficient in multicasting, it requires a lot of state to be held by the participating routers. So now the P routers are participating in the multicast LSPs, whereas where we had unicast LSPs, the P routers are not involved at all in those VPNs, whereas now the P routers are involved. So it's a lot more, if you like, intensive on the routers to maintain all this extra state. So this kind of selective is more intensive but more efficient as far as bandwidth goes. The previous, the inclusive, is less efficient, but it's a lot easier on the routers to maintain the state. So you've got the benefit of the selective in that we only send traffic to where there's receivers, but more state to maintain. And with the inclusive, you may send traffic on parts of the tree where there are no receivers, but there's a whole lot less state to maintain. So it's a scalability issue. Okay, so some of the requirements on the actual routers, we do require a tunnel interface pick on certain routers, customers first hop, and customers candidate RPs. All PE routers participating in the customer's multicast network will require that, except when using VRF table labels, and tunnel services needs to be enabled on the MX series routers. So we've kind of got that example of how that is enabled there. Alrighty, so the RFC actually provides a lot of possibilities, a lot of ways of going about doing this, and there's just a list of the things that are supported by Juniper. So what providers do is they take the RFC and they decide what parts or what features of it they're going to support. They don't necessarily support absolutely every possible feature that is available. There's a list of Junipers there. And we have got some configuration there. Okay, now I'm not going to go through the configuration because it's pretty boring just looking at code unless you're actually doing it. There is within our within the course, within the learning portal, within the MPLS course, there's a very good example, a number of videos that go through that in some detail as to how that is actually done. Unfortunately, we don't have a lab on it at this time, okay, which is good for you guys because in some way you don't have to do it. All right, it saves you work. It's quite a big lab. I know you got nothing to do. I know you guys are sitting around bored. Ah, gee, this course is so easy. Come on, give me something hard. Give me something hard. I get those complaints all the time. All right, just kidding. Yeah, so we used to do this lab. It's very, very intensive in that I think it's got around 13 different routers in the lab, and you get to configure all 13 of them. Yeah, like not just one, right, what we're doing now, or maybe two if you're doing the whole pod. You get to configure the whole 13. And the BGP stuff you got to do is nuts, all right? And just nuts. You're configuring route targets, you're doing filtering, you're doing a whole heap of stuff. It's great fun. Yeah. Yeah, but yeah, I haven't set it up yet because it's so we can only run nine routers on a server. Right? That's a server running 16 cores, 32 threads, with about 120 gig of RAM. Right, so these routers are very processor intensive. So I haven't had to figure out how to run 13 on them yet, but I will. I will at some point in my spare time figure out how to do that. All right, I know it's possible. All righty, so yeah, so unfortunately, guys, I'm really sorry, there is no lab on this. Okay, so, but there is a great tutorial in the up on the learning portal, which I love to refer to as Juniper Dragnet. I don't know if you guys ever saw that TV show Dragnet, but okay, you haven't, don't worry. Basically, just the way that the presenter of those particular labs just sounds like he's straight out of that show. Anyway, all right. So there we are. That's the configuration. I'm not going to delve into the configuration because we're not going to get to do it in any case. Alrighty. So that's just an overview of the MPLS config there, more configuration, a bit of monitoring there that we get to do. Yeah, fortunately we don't have a lab, but we'll get there. We'll get there. Okay. So main point here is that the purpose of this multicast MPLS is to distribute multicast traffic like IPTV and radio. Okay, now I have talked to service providers in Australia, and they have said that they are actually providing these services to radio stations that are looking for multicast. I haven't come across IPTV at this stage. All right, and that's probably the reason for it is we've just gone to digital transmission, and that happened about 10 years ago. So when that happened, the television broadcasters had to build brand new transmitters. So the lifespan of a transmitter is about, it's probably absolute tops about 30 years you get out of a transmitter. So probably I would expect over the next 20 years they will start to convert from broadcast to more IP-based delivery of their services. And it's just a case of we don't even have the internet infrastructure here in Australia to support that yet. We just don't have the bandwidth available to everybody to actually get television or to get IPTV. But over the next 10 years, I expect we will, and then we'll see stations start to change. Alrighty, guys. Who's going to be here after lunch? Anybody? All right, because I want to do an exam review. I just want to go through the exam, talk about, kind of what's in it, how to approach it, etc. Okay, so it'll probably take about half an hour. So we'll break for lunch, and we'll come back at 1, and we'll take about half an hour or so going through that. Okay, I'll answer any questions that you might have. Thank you.